So I'll continue my way of doing things. So I'll take another report from these collaborations between UNEP, DHI Center, CTCN, which is the Climate Technology Center and Network, and UNEP DTU partnership. It's called Climate Change Adaptation Technologies for Water, a Practitioner's Guide to Adaptation Technologies for Increased Water Sector Resilience. We are in the course on adaptation, or at least a series of podcasts on adaptation. Obviously, resilience is the biggest part of adaptation, and hence I include anything that builds resilience for the future in this series of podcasts. There are a few points. This is a very nice report, a bit old, but things remain the same in terms of the technologies and the way to do adaptation for the water sector to build resilience for the future. And there are lots of resources provided with links associated with water issues with too little water, too much water, and so on and so forth. So let's start with this schematic on 102 water adaptation technologies, climate change adaptation and water overview of challenges and responses. Integrated approaches to adaptation planning. This is the International Water Resource Management ideas, resources. They're schematic, so adaptation responses are starred here. So you can see that we have various components for water adaptation technologies that help deal with water and make it resilient. So we have disaster preparedness, unknown climate risks, too little water, too much water, water pollution, and sea level rise. Sea level rise tends to, affect groundwaters as well, salinization of groundwaters, and of course storm surge, inundation, and so on and so forth. So let's start with disaster preparedness. We have already learned a lot about early warnings and disaster response, which is part of the water adaptation as well. I have a whole course on subseasonal to seasonal forecasts and applications, where water is one of the applications, especially in terms of converting weather forecasts into advisories for agriculture, for example, and can be done for other parts of the water issues as well. Unknown climate risks, again, hazard and risk assessment and vulnerability assessment are required for adaptation. For too little water, we'll see a long table, but it's about water allocation, water augmentation, water efficiency and demand management, water storage, alternative water sources. When you have too little water, you have to really scamper around. And remember that there is always this nexus between food, water, health, energy, and so on that we have discussed. So we should always keep those nexuses in mind when we are doing adaptation in each sector. Too much water requires riverine flood protection, urban stormwater management, glacial lake outburst prevention, which is not easy, but nonetheless the great efforts are being made, because they are somewhat of a low frequency, high impact events, but the question is whether the frequencies are beginning to go up in terms of glacial lake outbursts with warming. Water pollution, of course, limiting nutrient leakage, mitigating pollution at source, flood proofing of water quality, and improved water treatment capacity. So water quality gets greatly affected by floods and results quickly in health issues, and of course that's part of the adaptation. Limiting water intrusion, so sea level rise, limiting water intrusion, built infrastructure for shoreline protection, green infrastructure for shoreline protection, accommodation and management. So we'll look at a table for each of these. And water is of course a very important sector, and this is very clear by looking at the number of parties that refer to an area or sector as a priority in adaptation actions communicated in their adaptation component of the originally it was called intended nationally determined contributions, but now they are just called nationally determined contributions. Each country submitted a plan to the Paris Agreement. It was found that they were not adequate, so most countries have updated their nationally determined contributions to kind of try to stay towards the global warming targets. Of course, we are not on track, but nonetheless. So water here tops in terms of the number of countries that have included as a sector in their nationally determined contributions. Agriculture comes up next, and energy is down there at 53 countries. So it gives you a sense of how each country, how most of the countries think of water as an important sector for their nationally determined contributions in reducing emissions, adaptation, mitigation, national adaptation plan, and so on. Okay, so water adaptation technology taxonomy, climate change adaptation technologies for water. We again said 102, so there must be a caption here which I removed, but nonetheless, we are looking at what we said before: unknown climate risks, too little water, too much water, and then we look at water pollution, sea level rise, and disaster preparedness. So under these we had unknown climate risks, hazard and risk assessment, and vulnerability assessment. We are kind of transferring the concepts across all the sectors, which is good. Vulnerability assessment comes up in every sector, which is in fact very critical, and then it has to be converted to socio-economic vulnerability as well. So there is vulnerability of the water sector or agricultural sector themselves to climate change, and then you have socio-economic vulnerabilities to water and agriculture as well, in terms of access, quantity, quality, nutrition, food security, water security, etc. Right? So unknown climate risks are always an issue. Hazard and risk assessment should include downscaling of climate model projections, disaster risk assessment using LiDAR, like radar, but light detection and ranging. Flood hazard assessment and mapping, drought risk assessment and mapping. Sound very simple, but data are needed at granularity to map them properly. Vulnerability assessment, of course, socioeconomic scenarios, as we said, for the future. Shared socioeconomic pathways of different levels of radiative forcing are used to do these. Climate change vulnerability assessments and decision scaling. All adaptation is local, all water adaptation is also local, but sometimes you have upstream water sources with users in the upstream and downstream demands, and they have to be coordinated as well, which we have looked at before under food security as well. Too little water, so we'll look at the table again, but it includes water allocation, water augmentation, water efficiency and demand management, water storage, alternative water sources. So under each we have few steps that we'll come back to. Too much water, as we said, has riverine flood protection, urban storm water management, and glacial lake outbursts. Here, for example, artificial lowering of glacial lakes to prevent outbursts. How do you do that? You have to basically drain the lakes and use the water appropriately without jeopardizing the water security of the people who depend on those lakes, typically upstream. If you think about rivers in the Himalayan region flowing into the Indian subcontinent, for example, the contribution of the glaciers to the rivers stream flows depends on where you are. Upstream there will be much higher contribution than downstream, where monsoon adds much more, and so on. So all these are important. Water pollution, as we said, limiting nutrient leakage, salt water intrusion, mitigating pollution at source, flood proofing for water quality, and improved water treatment capacities are important. Sea level rise, I'm repeating some of these, but it's okay, re-emphasizes the points, and there are additional points under each header that we are going to look at in terms of tables, as I said. Limiting salt water intrusion, built infrastructure for shoreline protection, green infrastructure for shoreline protection, accommodation and management. So green infrastructure and built infrastructure, what is the relation? Well, you use things like nature-based solutions, artificial reefs, etc. in the green infrastructure, and you make them adaptive as well. And built infrastructure as adaptations to sea level rise again have to be responsive to changing sea level rise. But we have also talked about this before, saying that let's say for a city like Mumbai, when you have sea level projections, There are obviously uncertainties in the projections, but how you plan built infrastructure for adaptation often doesn't depend on the uncertainties in the projection. It depends on the finances, the cost benefit ratios. If you want to protect against 20 centimeter rise versus half a meter rise versus 1 meter rise, how much does each one cost, and how the community or the local government or the central government decide how much money it wants to put into putting up built infrastructure to protect against sea level rise, whether it's for water and salinity intrusion or just protecting people themselves and so on. Okay, disaster preparedness, early warnings are a critical component with flood forecasting, drought forecasting, early warning for floods, landslide and mud flow warning systems and so on, which we will come back to. And disaster response, of course, stacking of sandbags combined with the use of groundwater improvement technology. It's kind of a low-level, no-regret decision, for example. But there are other investments needed in flood shelters and social media application for disaster response and mapping, national and community disaster management plans. So crowdsourcing of information for floods is very useful now, being done in many places where Twitter's, now called X, and other media comments from people are used to track floods and then evolve the response in near real time. Okay, India has now become somewhat of a model in terms of good practices for how to do national disaster management. They have reduced mortalities for cyclones, heat waves, and other things by designing proper strategies, combining with early warning systems and so on, which is great for other global south countries as well. Okay, maybe, yeah, let me finish this one as well. Adaptation technologies for tackling unknown climate risks. So there is adaptation response, technologies, and description. And this report is very nice for technology description brief. It provides a link for each item. I'm not going to click on them, but you can go ahead and do that. And in fact, in some of the tables, I'm going to take out this column just to make it better for displaying the text. So you have technologies. So in the adaptation response, we have hazard and risk assessment, which requires technologies like downscaling of climate model projections, disaster risk assessment using LiDAR, flood hazard assessment and mapping, drought risk assessment and mapping. So you have here methods of estimating local scale climate change impacts based on information derived from regional and global climate models. Downscaling is very common now, and everybody is doing it, and it's obvious now that the models will only get you down to at best, let's say, kilometer scale, even when regional downscaling is done with dynamic models. And then typically AI and artificial intelligence and machine learning are used to bring that information further down to neighborhood levels, street levels, to manage climate risks for flood or whatever else. Okay, so that's very common, and you can read the technology description there. Disaster risk assessment using LiDAR, light detection and ranging, is a remote sensing method that can be used to generate detailed maps of topography and retrieve digital elevation data necessary for flood modeling and vulnerability and risk analysis. So DEMs, or digital elevation maps, are needed to bring water into the urban centers or wherever else to see how deep the waters are and how decisions have to be taken about, let's say, evacuating a school or a hospital, closing down streets, or rerouting traffic, and ensuring groundwater doesn't get contaminated, water quality issues, and so on and so forth. Flood hazard assessment and mapping. So technologies used to identify areas at risk of flooding and consequently to improve flood risk management and disaster preparedness. Typically look at the expected extent and depth of flooding in a given location based on various scenarios, such as return periods, so 100-year events, 50-year events, etc. So most of the urban centers are designed over a long period of time for certain rainfall ranges and return periods, but climate change shortens the return period. 100-year events may begin to occur every 50 years or shorter, and similarly 50-year event may become more frequent. So these have to be used in flood hazard assessment and mapping, and design adaptation responses for hazard risk and assessment. Drought risk assessment and mapping, surely a key element of drought management, as it helps identify the areas most at risk of droughts, allowing communities to plan as well as prepare for and mitigate possible impacts. Now we have also the idea of flash droughts, so they are also rapidly evolving droughts as opposed to older droughts which used to evolve over time, as opposed to floods which are very acute events. Droughts used to be kind of grow over time, but now because of the warming, responses in soil moisture, extraction of groundwater, etc., are producing what we call flash droughts, which are obviously the rates at which the droughts get very severe, going from, let's say, meteorological drought to agricultural or ecological or hydrological droughts. Okay. For vulnerability assessment, we have socioeconomic scenarios, climate change vulnerability assessment, and decision scaling. Just to read off a few sentences here, socioeconomic scenarios are various models that represent assumed developments in key socioeconomic drivers. The scenarios are used to characterize the social and economic forces driving climate change, in addition to projecting the vulnerability and or adaptive capacity of socioeconomic systems to the impacts of climate change. There are uncertainties, but these what-if scenarios give you the envelope that you can expect in terms of socioeconomic vulnerabilities and risks. So you have hazards, risks, hazards, vulnerabilities, exposure, and responses, which are going to define the risks. So when you do vulnerability assessment, you want to identify risks and adaptation gaps as well. Of course, there is always cost-benefit ratios to worry about, as we saw before. Climate change vulnerability assessments establish understanding of the extent to which changing climate will affect the system in question. Vulnerability assessment methods go beyond the immediate hazards stemming from the changes in temperature and rainfall, which is exposure, assessing also the characteristics of the system itself, so sensitivity, as well as its ability to deal with the anticipated impacts, so adaptive capacity. Okay, there is more text here that you can go back and read. A nice report available online. Decision scaling is important approach to climate risk and vulnerability assessment that couples inputs from stakeholders and climate projections. Central to decision scaling is the use of data analytics coupled with stakeholder engagement to understand key sensitivities and uncertainties, and identification of robust response approaches. So now I'll definitely stop because this is already 18 minutes long, but that's okay. So we'll come back and continue and wrap up this report in a few podcasts. Okay.